Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Hermitian operators. Let's begin. In quantum mechanics, any physical quantity are expressed in terms of the operators that can be written in terms of linear operator. In quantum mechanics, a physical quantity let's say Q is represented by a linear operator Q cap, and the expectation value of that of Q, the expectation value of Q in state psi is the wave function. In that of case, let psi is normalized, then the expectation value is given by integration from minus infinity to plus infinity psi star Q cap psi dqr, where psi is a normalized wave function. Then the expectation value of that physical quantity or that of physical observable is written like this. Since the expectation value of that of Q in that of state psi is a real quantity, that is why the expectation value here, the expectation value of Q in the state psi is a real quantity. Thus, the expectation value of Q is same as the conjugate of that expectation value. Since it is real, its complex conjugate it same, but that complex conjugate, the complex conjugate of that observable Q, in place of Q we write minus infinity to plus infinity psi star Q cap psi dqr, and its expectation that gives rise to integration from minus infinity to plus infinity Q cap psi star psi dqr. Now, comparing these two equations, here Q, expectation of Q is that one, here expectation of Q star is that one. Since the expectation of Q is same as that of complex conjugate of that of expectation of that same observable Q, then these two equations are Same, taking equation number 1, here we take equation number 2, therefore that integral is same as this integral, that is integration from minus infinity to plus infinity psi star q cap psi dqr is equal to integration from minus infinity to plus infinity q cap psi star psi dqr. And equation number 3, that means any operator which represent a physical observable must be Hermitian. From that we conclude that any operator which represent a physical observable must be Hermitian, and that condition is the condition for Hermiticity, that is the condition for Hermiticity. And that physical observable is said to be Hermitian. If that physical observable satisfy that Hermiticity condition, then we can say that physical observable is Hermitian. That means if that operator q cap, here that operator q cap is said to be Hermitian, the above equation 3 can be satisfied by an operator q cap satisfy that condition for Hermiticity, then that satisfying that operator q cap is called Hermitian operator, that is the condition for Hermiticity, and the operator which satisfy that condition is known as the condition for Hermiticity, that is known as the Hermitian operator. Another way to define that Hermitian operator, how we define the Hermitian operator, look here, how we define, if condition, if q cap is Hermitian, in the sense it is satisfy the condition for Hermiticity. If q cap is Hermitian and two wave function psi 1 and psi 2 are state functions, then the equations like integration from minus infinity to plus infinity q cap psi 1 star psi 2 dqr is equal to integration from minus infinity to plus infinity psi 1 star q cap psi 2 dqr. That equation is satisfied. And again another form that also can be written like this: integration from minus infinity to plus infinity q cap psi 2 star psi 1 dqr is equal to integration from minus infinity to plus infinity psi 2 star q cap psi 1 dqr. These two equations are satisfy that Hermitian operator q cap. These two equations combinedly, we can say these two equations are the generalization of the definition of Hermitian operator. Hermitian operator. The generalization of the definition of Hermitian operator. Here all about the definition towards Hermitian operators. What is that of condition for hermiticity, and how we can say operator is said to be Hermitian. First, we take that operator is in the form of a linear operator. That's why we can say either it's Hermitian or not. Then, if psi 1 and psi 2 are the two state functions and q cap is Hermitian, then it is satisfy these two conditions. That is the generalization of the definition towards Hermitian operators. Now, our aim is to prove the hermiticity of a position and momentum operator. That means the position and momentum operators are said to be Hermitian. How we can say? First, hermiticity of a position operator. For normalized wave function psi x, we take for normalized wave function psi x, psi of x, then the expectation value of x, then the expectation value of x is given by the expectation value of x is given as integration from minus infinity to plus infinity psi star x cap psi dqr, integration from minus infinity to plus infinity, that can be written like this: x cap psi star psi dqr, as x cap is equal to x cap star. Since x is real, that means that one is real, is equal to integration from minus infinity to plus infinity, x cap is x psi star psi dq, sorry that not r, that is dqx, just only dx, we consider one dimensional, that is only dx, sorry for that, that is only dx for one dimensional case. If that one is 3 dimension, just we consider dq. That value is expectation conjugate. Therefore, Hence x cap, that is the position operator, is said to be Hermitian. As we know, if q is equal to conjugate of that of q star, expectation of q is same as that of conjugate of that of expectation value, then that operator is said to be Hermitian. Therefore, the position operator is Hermitian, is proved. Again, hermiticity of that of momentum operator, how we can prove? Again, same procedure we have to take. For momentum operator, for normalized wave function, for normalized wave function psi of x, the expectation value of px is given as the expectation value of px, that is integration from minus infinity to plus infinity psi star px cap psi dx. We consider in one dimensional case, therefore we treat it as x, that is integration from minus infinity to plus infinity psi star px cap h cross by I del psi by del x dx is equal to h cross by I integration from minus infinity to plus infinity psi star del psi by del x dx. Two functions are multiplied with each other. Here we use the by parts rule. H cross by I by parts rule, that is psi star psi from the limit minus infinity to plus infinity minus integration from minus infinity to plus infinity del psi star del x psi dx. This term will be 0, that is minus h cross by I integration from minus infinity to plus infinity del psi star by del x psi dx. Here minus infinity to plus infinity h cross by I del psi by del x conjugate psi dx, and this one is continued minus infinity to plus infinity h cross by I del by del x psi star psi dx. Integration from minus infinity to plus infinity psi star, that operate over this, we can say the conjugate of this. This is the conjugate px cap star psi dx, that is integration from minus infinity to plus infinity, that is px psi star combining these two psi dx. that is the expectation of Px conjugate. So, we can say that momentum operator is Hermitian, hence Px cap is Hermitian. Here the proof of hermiticity of that opposition operator, and here the hermiticity of momentum operator. Now, two problems related to Hermitian operators. One is prove that the vector momentum operator P vector cap is Hermitian. Same way we have to prove that one. Let us say solution here. For normalized wave function psi r, for normalized wave function psi r, the value of the expectation value of P vector, the momentum operator P vector, the P vector, sorry, not x, we consider it in 3-dimensional case, that is P vector expectation will be integration from minus infinity to plus infinity psi star P vector cap psi dqr is equal to integration from minus infinity to plus infinity psi star P vector cap, it is h cross by I grad psi dqr, h cross by I integration from minus infinity to plus infinity psi star grad psi dqr. Here h cross by I integration from minus infinity to plus infinity, that particular term can be written like this: grad of psi star. Grad of psi star means the derivative of first term, second term treated as constant, plus the derivative of second term, first term treated as constant. That means psi grad psi star plus psi star grad psi star, psi star grad psi. Our aim is to find out that one. Therefore, we have to eliminate psi grad psi star here, then we get that term dqr. Okay, separating these two, h cross by I integration from minus infinity to plus infinity grad psi star dqr minus h cross by I integration from minus infinity to plus infinity psi grad psi star dqr. Here we have to use the Gauss divergence theorem to that of first term of that of RHS of above equation, that change to h cross by I closed curve integration over that of S, that volume integration change to surface integration psi star ds minus h cross by I integration from minus infinity to plus infinity psi grad psi star dqr. Here we using Gauss divergence theorem to the first term of RHS of above equation. That term will be 0. Why that term will be 0? Since psi of f of x is 0 for x tends to plus minus infinity. For x plus minus infinity, psi of f of x will be 0. That is why closed curve integration over S psi star ds is equal to 0. Only that term exists. Minus h cross by I integration from minus infinity to plus infinity psi grad psi star dq. Here minus infinity to plus infinity h cross by I grad psi star psi dq. This particular term can be written like this: minus infinity to plus infinity, that is the momentum vector operator psi star psi dq. That is nothing, that is the expectation of conjugate. So the momentum operator star is Hermitian. The vector momentum operator is Hermitian. Now another question: prove that the Hamiltonian operator that is h cap is equal to p vector cap square divided by 2m plus v cap, that is the potential and the function of r, is Hermitian. Again we prove that one by using the previous methods. For normalized state wave function, psi r, the expectation value of Hamiltonian operator h is integration from minus infinity to plus infinity psi star h cap psi dq is equal to integration from minus infinity to plus infinity psi star cap square divided by 2m plus v psi dq. 1 by 2m integration from minus infinity to plus infinity psi star e cap square psi dq plus integration from minus infinity to plus infinity psi star b cap psi dq. 1 by 2m integration from minus infinity to plus infinity p vector cap psi star, and again p vector cap psi dq plus integration from minus infinity to plus infinity psi star b cap psi d cube, just p cap square psi. Here integration from minus infinity to plus infinity, p vector square divided by 2m act over psi star psi d cube plus integration from minus infinity to plus infinity v cap psi star psi d cube is equal to integration from minus infinity to plus infinity f psi divided by 2m plus v over psi its complex conjugate psi d cube. Here as v is real in the sense its complex conjugate is also a real quantity, that is the Hamiltonian operator. Integration from minus infinity to plus infinity h cap psi star psi d cube, that can be further written in terms of complex conjugate as minus infinity to plus infinity h cap psi star d cube whole conjugate. In that of term, the expectation of h and its conjugate. So we can say h cap, that is the Hamiltonian operator, is Hermitian. The Hamiltonian operator is Hermitian. So with the help of this video lecture, we understand what is Hermitian operators and condition for hermiticity and how a operator is said to be Hermitian. Then we prove the generalization of definition towards Hermitian operator and prove hermiticity of position operator and hermiticity of momentum operator, and two problems related to that Hermitian operator, that is proof that the vector momentum operator is Hermitian and the Hamiltonian operator is Hermitian. So with this useful and informative notes, let me wind up this session. Thank you.